Learning objectives. In this chapter, the user will learn the following in detail: bubble sort, insertion sort, selection sort, shell sort, faster methods, tree sort, heap sort, merge sort, quicksort, linear timer sorting, counting or enumeration sort, radic sort, bucket sort, bubble sort. Perhaps the simplest sorting method one can devise is an algorithm called bubble sort. The basic idea behind bubble sort is to imagine that the records to be sorted are kept in an array held vertically. The records with low key values are light and bubble up to the top. We make repeated passes over the array from bottom to top. If two adjacent elements are out of order, that is, if the lighter one is below, we reverse them. The effect of this operation is that on the first pass, the lightest record, that is, the record with the lowest key value, rises all the way to the top. On the second pass, the second lowest key value rises to the second position, and so on. We need not, on pass 2, try to bubble up to position 1, because we know the lowest key already resides there. In general, pass I need not try to bubble up past position I. Bubble sort algorithm shown in below figure. Assuming A is an array, it has the elements 1 up to n of record type and n is the number of records. Assume here that one field called key holds the key value for each record. The procedure swap is used in many sorting algorithms is shown in below figure. Example, the following figure shows a list of famous volcanoes and a year in which each erupted. For this example, we shall use the following type definitions, which is shown in below figure in our sorting programs. The bubble sort algorithm applied to the list of above figure sorts the list in alphabetical order of names if the relation less than or equals on objects of this key type is the ordinary lexicographic order. As shown in below, the 5 passes made by the algorithm when n equals 6. The lines indicate the point above which the names are known to be the smallest in the list and in the correct order. However, after I equals 5, when all but the last record is in its place, the last must also be in its correct place and the algorithm stops. At the start of the first pass, St. Helens bubbles past Vesuvius, but not past Agon. And the remainder of that pass, Agon bubbles all the way up to the top. In the second pass, Etna bubbles as far as it can go to position 2. In the third pass, Krakatoa bubbles past Pele, and the list is now in lexicographically sorted order, although, according to the algorithm, 2 additional passes are made. Time complexity of the bubble sort. Bubble sort takes big O of n square time and will take big omega of n square time on some. In fact, on most input sequences of n elements. Consider bubble sort algorithm. No matter what record type is, swap takes a constant time. Thus, lines 3 and 4 of bubble sort algorithm takes at most C1 time units for some constants C1. Hence, for a fixed value of I, the loop of lines 2 to 4 takes at most C2 of n minus I steps for some constant C2. The later constant is somewhat larger than C1 to account for decrementation and testing of J. Consequently, the entire program takes at most as shown steps where the term C3n accounts for incrementation and testing I. As the later formula does not exceed C2 by 2 plus C3 into n square for n greater than or equals 1, we see that the time complexity of bubble sort is big O of n square. The algorithm requires big omega of n square steps, since even if no swaps are ever needed, that is, the input happens to be already sorted, the test of line 3 is executed n into n minus 1 by 2 times. Faster sorting methods. Some faster sorting methods are tree sort, heap sort, merge sort, and quicksort. Tree sort. A tree sort is a sort algorithm that builds a binary search tree from the elements to be sorted and then traverses the tree in order so that the elements come out in sorted order. Its typical use is sorting elements adaptively. After each insertion, the set of elements seen so far is available in sorted order. Efficiency. Adding one item to a binary search tree is an average and big O of log n process in big O notation. So adding n items is an big O of n log n process, making tree sort a fast sort. But adding an item to an unbalanced binary tree needs big O of n time in the worst case, when the tree resembles a linked list degenerate tree, causing a worst case of big O of n square for this sorting algorithm. This worst case occurs when the algorithm operates on an already sorted set, or one that is nearly sorted. Expected big O of log n time can however be achieved in this case by shuffling the array. The worst case behavior can be improved upon by using a self-balancing binary search tree. Using such a tree, the algorithm has an big O of n log n worst case performance, thus being degree optimal for a comparison sort. When using a splay tree as the binary search tree, the resulting algorithm called splay sort has the additional property that it is an adaptive sort, meaning that its running time is faster than big O of n log n for inputs that are nearly sorted. Example: the following tree sort algorithm in pseudocode accepts an array of comparable items and outputs the items in ascending order. Heap sort. Priority queues can be used to sort in big O of n log n time. The algorithm based on this idea is known as heap sort and gives the best big O running time. The basic strategy is to build a binary heap of n elements. This stage takes big O of n time. We then perform n delete min operations. The elements leave the heap smallest first in sorted order. By recording these elements in a second array and then copying the array back, we sort n elements. Since each delete min takes big O of log n time, the total running time is big O of n log n. The main problem with this algorithm is that it uses an extra array. Thus, the memory requirement is doubled. This would be a problem in some instances. Notice that the extra time spent copying the second array back to the first is only big O of n, so that this is not likely to affect the running time significantly. The problem is space. A clever way to avoid using a second array makes use of the fact that after each delete min, the heap shrinks by 1. Thus, the cell that was lost in the heap can be used to store the element that was just deleted. As an example, suppose we have a heap with 6 elements. The first delete min produces A1. Now the heap has only 5 elements, so we can place A1 in position 6. The next delete min produces A2. Since the heap will now only have 4 elements, we can place A2 in position 5. Using this strategy, after the last delete min, the array will contain the elements in decreasing sorted order. If we want the elements in the more typical increasing sorted order, we can change the ordering property so that the parent has a larger element than the child. Thus, we have a max heap. In our implementation, we will use a max heap but avoid the actual ADT for the purpose of speed. As usual, everything is done in an array. The first step builds the heap in linear time. We then perform n-1 delete maxes by swapping the last element in the heap with the first, decrementing the heap size and percolating down. When the algorithm terminates, the array contains the elements in sorted order. For instance, consider the input sequences 31, 41, 59, 26, 53, 58, and 97. The resulting heap is shown in below figure. Below figure shows the heap that results after the first delete max. As the figures imply, the last element in the heap is 31. 97 has been placed in a part of the heap array that is technically no longer part of the heap. After 5 more delete max operations, the heap will actually have only one element, but the elements left in the heap array will be in sorted order. The code to perform heap sort is given in below figure. The slight complication is that, unlike the binary heap, where the data begins at array index 1, the array for heap sort contains data in position 0. Thus, the code is a little different from the binary heap code. The changes are minor. Analysis of heap sort. The first phase, which constitutes the building of the heap, uses less than 2n comparisons. In the second phase, the ith delete max uses at most less than 2 into flow of log n minus I plus 1 comparisons, for a total of at most 2n log n minus big O of n comparisons, assuming here n greater than or equals 2. Consequently, in the worst case, at most 2n log n minus big O of n comparisons are used by heap sort. Experiments have shown that the performance of heap sort is extremely consistent. On average, it uses only slightly fewer comparisons than the worst case bound suggests. For many years, nobody had been able to show non-trivial bounds on heap sort's average running time. The problem, it seems, is that successive delete max operations destroy the heap's randomness, making the probability arguments very complex. Eventually, another approach proved successful. Merge sort. Merge sort runs in big O of n log n worst case running time, and the number of comparisons used is nearly optimal. It is a fine example of recursive algorithm. The fundamental operation in this algorithm is merging two sorted lists, because the lists are sorted. This can be done in one pass through the input, if the output is put in a third list. The basic merging algorithm takes two input arrays, A and B, an output array, C, and three counters, A counter, B counter, and C counter, which are initially set to the beginning of their respective arrays. The smaller of A counter and B of B counter is copied to the next entry in C, and the appropriate counters are advanced. When either input list is exhausted or the remainder of the other list is copied to C. An example of how the merge routine works is provided for the following input. If the array A contains 1, 13, 24, and 26, and B contains 2, 15, 27, and 38, then the algorithm proceeds as follows. First, a comparison is done between 1 and 2. 1 is added to C, and then 13 and 2 are compared. 2 is added to C, and then 13 and 15 are compared. 13 is added to C, then 24 and 15 are compared. 15 is added to C, then 24 and 27 are compared. Now 24 is added to C, then 26 and 27 are compared. 26 is added to C, and the A array is exhausted. Then the remainder of the B array is then copied to C. The time to merge two sorted lists is clearly linear because at most n-1 comparisons are made, where n is the total number of elements. To see this, note that every comparison adds an element to C except the last comparison, which adds at least 2. If n equals 1, there is only one element to sort, otherwise recursively merge sort the first half and the second half. This gives two sorted halves, which can then be merged together using the merging algorithm described above. For instance, to sort the 8-element array for the given sequence, we recursively sort the first 4 and the last 4 elements and obtaining the result. Then we merge the two halves, obtaining the final list as shown here. This algorithm is a classic divide and conquer strategy. The problem is divided into smaller problems and solved recursively. The conquering phase consists of patching together the answers. Divide and conquer is a very powerful use of recursion. An implementation of merge sort is provided in the following figure. The 1-parameter merge sort is just a driver for the 4-parameter recursive merge sort. The merge routine is subtle. If a temporary array is declared locally for each recursive call of merge, then there would be log n temporary arrays active at any point. A close examination shows that since merge is the last line of merge sort, there only needs to be one temporary array active at any point, and that the temporary array can be created in the public merge sort driver. Further, we can use any part of the temporary array. We will use the same portion as the input array A. Below figure shows the implementation of the merge routine. Analysis of merge sort. Merge sort is a classic example of the techniques used to analyze recursive routines. We have to write a recurrence relation for the running time. Assume that n is a power of 2 so that we always split into even halves. For n equals 1, the time to merge sort is constant, which we will denote by 1. Otherwise, the time to merge sort n numbers is equal to the time to do 2 recursive merge sorts of size n by 2 plus the time to merge, which is linear. The following equations say this exactly. T of 1 equals 1, T of n equals 2T of n by 2 plus n. This is a standard recurrence relation which can be solved several ways. We will show two methods. The first idea is to divide the recurrence relation through by n. The reason for doing this will become apparent soon. This yields T of n by n equals T of n by 2 by n by 2 plus 1. This equation is valid for any n that is a power of 2. So we may also write T of n by 2 by n by 2 equals T of n by 4 by n by 4 plus 1. And T of n by 4 by n by 4 equals T of n by 8 divided by n by 8 plus 1. It goes up to T of 2 by 2 equals T of 1 by 1 plus 1. Now add up all the equations. This means that we add all of the terms on the left hand side and set the result equal to the sum of all of the terms on the right hand side. Observe that the term T of n by 2 divided by n by 2 appears on both sides and thus cancels. In fact, virtually all the terms appear on both sides and cancel. This is called telescoping a sum. After everything is added, the final result is T of n by n equals T of 1 by 1 plus log n. Because all of the other terms cancel and there are log n equations, and so all the ones at the end of these equations add up to log n. Multiplying through by n gives the final answer. T of n equals n log n plus n equals big O of n log n. Notice that if we did not divide through by n at the start of the solutions, the sum would not telescope. This is why it was necessary to divide through by n. An alternative method is to substitute the recurrence relation continually on the right hand side. We have T of n equals 2T of n by 2 plus n. Since we can substitute n by 2 into the main equation, 2T of n by 2 equals 2 into 2 of t by n by 4 plus n by 2 equals 4T of n by 4 plus n. We have T of n equals 4T of n by 4 plus 2n. Again, by substituting n by 4 into the main equation, we see that 4T of n by 4 equals 4 into 2T of n by 8 plus n by 4 equals 8T of n by 8 plus n. So we have T of n equals 8T of n by 8 plus 3n. Continuing in this manner, we obtain T of n equals 2 power k into T of n by 2 power k plus k into n. Using k equals log n, then we obtain T of n equals n into t of 1 plus n log n equals n log n plus n. The first method tends to produce scrap work that fits better on a standard 8.5 into 11 sheet of paper, leading to fewer mathematical errors, but it requires a certain amount of experience to apply. The second method is more of a brute force approach. Recall that we have assumed n equals 2 power k. The analysis can be refined to handle cases when n is not a power of 2. The answer turns out to be almost identical. Although merge sort's running time is big O of n log n, it has the significant problem that merging two sorted lists uses linear extra memory. The additional work involved in copying to the temporary array and back throughout the algorithm slows the sort considerably. This copying can be avoided by judicially switching the roles of A and temporary array at alternate levels of the recursion. A variant of merge sort can also be implemented on recursively. The running time of merge sort when compared with other big O of n log n alternatives depends heavily on the relative costs of comparing elements and moving elements in the array and the temporary array. These costs are language dependent. For instance, in Java, when performing a generic sort using a comparator, an element comparison can be expensive because comparisons might not be easily inlined, and thus the overhead of dynamic dispatch would slow things down. But moving elements is cheap because they are reference assignments rather than copies of larger objects. Merge sort uses the lowest number of comparisons of all the popular sorting algorithms and thus is a good candidate for general purpose sorting in Java. In fact, it is the algorithm used in the standard Java library for generic sorting. On the other hand, in classic C++, in a generic sort, copying objects can be expensive if the objects are large, while comparing objects often is relatively cheap because of the ability of the compiler to aggressively perform inline optimization. In this scenario, it might be reasonable to have an algorithm use a few more comparisons if we can also use significantly fewer data movements. Quicksort. Quicksort is the fastest generic sorting algorithm. Its average running time is big O of n log n. It is very fast, mainly due to a very tight and highly optimized inner loop. It has big O of n square worst case performance. By combining Quicksort with Heap Sort, we can achieve Quicksort's fast running time on almost all inputs, with Heap Sort's big O of n log n worst case running time. The Quicksort algorithm is simple to understand and prove correct. Although for many years it had the reputation of being an algorithm that would in theory be highly optimized, but in practice was impossible to code correctly. Like merge sort, Quicksort is a divide and conquer recursive algorithm. Let us begin with the following simple sorting algorithm to sort a list. Arbitrarily choose any item and then form three groups. Those smaller than the chosen item, those equal to the chosen item, and those larger than the chosen item. Recursively sort the first and third groups and then concatenate the three groups. The result is guaranteed by the basic principles of recursion to be a sorted arrangement of the original list. A direct implementation of Quicksort is shown in below figure, and its performance is generally speaking quite respectable on most inputs. In fact, if the list contains large numbers of duplicates with relatively few distinct items, then the performance is extremely good. In order to do better, we must avoid using significant extra memory and have inner loops that are clean. Thus, Quicksort is commonly written in a manner that avoids creating the second group, the equal items, and the algorithm has numerous subtle details that affect the performance. Therein lies the complications. The most common implementation of Quicksort is classic Quicksort, in which the input is an array and in which no extra arrays are created by the algorithm. The classic Quicksort algorithm to sort an array S consists of the following four steps. Step 1. If the number of elements in S is 0 or 1, then return. Step 2. Pick any element V in S. This is called the pivot. Step 3. Partition S minus V, the remaining elements in S, into two disjoint groups. S1 is a set which contains X belongs to S minus V, X less than or equals V. And S2 is the set which contains X belongs to S minus V, such that X greater than or equals V. Step 4. Return quicksort of S1 followed by V followed by quicksort of S2. Since the partition step ambiguously describes what to do with elements equal to the pivot, this becomes a design decision. Part of a good implementation is handling this case as efficiently as possible. Hope that about half the elements that are equal to the pivot go into S1 and the other half into S2, much as we like binary search trees to be balanced. The below figure shows the action of quicksort on a set of numbers. The pivot is chosen by chance to be 65. The remaining elements in the set are partitioned into two smaller sets. Recursively sorting the set of smaller numbers yields 0, 13, 26, 31, 43 and 57 by Rule 3 of recursion. The set of large numbers is similarly sorted. The sorted arrangement of the entire set is then trivially obtained. It should be clear that this algorithm works, but it's not clear why it's any faster than merge sort. It recursively solves two subproblems and requires linear additional work. Step 3. But the subproblems are not guaranteed to be of equal size, which is potentially bad. The reason that quicksort is faster is that the partitioning step can actually be performed in place and very efficiently. This efficiency more than makes up for the lack of equal-sized recursive calls. There are many ways to implement steps 2 and 3. The method presented here is the result of extensive analysis and empirical study and represents a very efficient way to implement quicksort. Partitioning strategy. The first step is to get the pivot element out of the way by swapping it with the last element. I starts at the first element and J starts at the next to last element. If the original input was the same as before, the following figure shows the current situation. Partitioning stage wants to do is to move all the small elements to the left part of the array and all the large elements to the right part. Small and large are related to the pivot. While I is to the left of J, move I right, skipping over elements that are smaller than the pivot. Move J left, skipping over elements that are larger than the pivot. When I and J have stopped, I is pointing at a large element and J is pointing at a small element. If I is to the left of J, those elements are swapped. The effect is to push a large element to the right and a small element to the left. In the example above, I would not move and J would slide over one place. This situation is as follows. We then swap the elements pointed to by I and J and repeat the process until I and J cross. At this stage, I and J have crossed, so no swap is performed. The final part of the partitioning is to swap the pivot element with the element pointed to by I. After swap with pivot is shown in this figure. When the pivot is swapped with I in the last step, we know that every element in a position P less than I must be small. This is because either position P contained a small element to start with or the large element originally in position P was replaced during a swap. A similar argument shows that elements in positions P greater than I must be large. If both I and J stop, there will be many swaps between identical elements. The positive effect is that I and J will cross in the middle. So when the pivot is replaced, the partition creates two nearly equal subarrays. The merge sort analysis tells us that the total running time would then be big O of n log n if neither I nor J stops, and code is present to prevent them from running off the end of the array. No swaps will be performed. Although this seems good, A correct implementation would then swap the pivot into the last spot that I touched, which would be the next to last position, or last, depending on the exact implementation. This would create very uneven subarrays. If all the elements are identical, the running time is big O of n square. The effect is the same as using the first element as a pivot for pre-sorted input. Thus, we find that it is better to do the unnecessary swaps and create even subarrays than to risk wildly uneven subarrays. Therefore, we will have both I and j stop if they encounter an element equal to the pivot. This turns out to be the only one of the 4 possibilities that does not take quadratic time for this input. Small arrays. For very small arrays, n less than or equals 20, Quicksort does not perform as well as insertion sort. Furthermore, because Quicksort is recursive, these cases will occur frequently. Actual Quicksort routines. The general form of the routines will be to pass the array and the range of the array left and right to be sorted. The first routine to deal with is pivot selection. The easiest way to do this is to sort A of left, A of right and A of center in place. This has the extra advantage that the smallest of the 3 winds up in A of left, which is where the partitioning step would put it anyway. The largest winds up in A of right, which is also the correct place since it is larger than the pivot. Therefore, we can place the pivot in A of right minus 1 and initialize I and j to left plus 1 and right minus 2 in the partition phase. Because A of left is smaller than the pivot, it will act as a sentinel for j. Thus, we do not need to worry about j running past the end. Since I will stop on elements equal to the pivot, storing the pivot in A of right minus 1 provides a sentinel for I. The code in below figure does the median of 3 partitioning with all the side effects described. It may seem that it is only slightly inefficient to compute the pivot by a method that does not actually sort A of left, A of center, and A of right, but surprisingly, this produces bad results. The Quicksort routine is shown in below figure. It includes the partitioning and recursive calls. There are several things worth noting in this implementation. Line 16 initializes I and j to 1 past their correct values so that there are no special cases to consider. This initialization depends on the fact that median of 3 partitioning has some side effects. This program will not work if you try to use it without change with a simple pivoting strategy, because I and j start in the wrong place and there is no longer a sentinel for j. The swapping action at line 22 is sometimes written explicitly for speed purposes. For the algorithm to be fast, it is necessary to force the compiler to compile this code inline. Many compilers will do this automatically if swap is declared using inline, but for those that do not, the difference can be significant. Finally, lines 19 and 20 show why Quicksort is so fast. The inner loop of the algorithm consists of an increment or decrement by 1, which is fast, a test and a jump. There is no extra juggling as there is in merge sort. Analysis of Quicksort. The running time of Quicksort is equal to the running time of the 2 recursive calls plus the linear time spent in the partition. This gives the basic Quicksort relation T of n equals T of I plus T of n minus I minus 1 plus C into n, where I equals modulus of S1 is the number of elements in S1. We will look at 3 cases. Worst case analysis. The total cost of all the partitions in recursive calls at depth d must be at most n, since the recursion depth is at most n. This gives an big O of n square, worst case bound for Quicksort. T of n equals T of 1 plus C into summation of I equals 2 to n I equals big theta of n square. Best case analysis. In the best case, the pivot is in the middle. To simplify the math, we assume that the 2 subarrays are each exactly half the size of the original. And although this gives a slight overestimate, this is acceptable because we are only interested in a big O answer. T of n equals Cn log n plus n equals big theta of n log n. Average case analysis. This is the most difficult part. For the average case, we assume that each of the sizes for S1 is equally likely and hence has probability 1 by n. This assumption is actually valid for our pivoting and partitioning strategy, but it's not valid for some others. Partitioning strategies that do not preserve the randomness of the subarrays cannot use this analysis. Interestingly, these strategies seem to result in programs that take longer to run in practice. T of n equals big O of n log n. Insertion sort. The ith pass, we insert the ith element, a of I, into its rightful place among a of 1 up to a of I minus 1, which were previously placed in sorted order. After doing this insertion, the records occupying a of 1 to a of I are in sorted order. That is, we execute the following code. To make the process of moving a of I easier, it helps to introduce an element a of 0, whose key has a value smaller than that of any key among a of 1 up to a of n. We shall postulate the existence of a constant negative infinity of type key type that is smaller than the key of any record that would appear in practice. If no constant negative infinity can be used safely, when deciding whether to push a of I up before position j, check first whether j equals 1, and if not, compare a of I, which is now in position j, with a of j minus 1. The complete program is shown in below figure. Example of insertion sort. The initial list shown in below figure and the result of the pauses of insertion sort for I equals 2, 3, it goes up to 6. The pauses of insertion sort shown in below figure. After each pass, the elements above the line are guaranteed to be sorted relative to each other, although their order bears no relation to the records below the line, which will be inserted later. Time complexity of the insertion sort. Insertion sort takes big O of n square time and will take big omega of n square time on some, in fact, on most input sequences of n elements. The while loop of lines 4 to 6 of insertion sort cannot take more than big O of I steps, since j is initialized to I at line 3 and decreases each time around the loop. The loop terminates by the time j equals 1, since a of 0 is negative infinity, which forces the test of line 4 to be false when j equals 1. We may conclude that the for loop of lines 2 to 6 takes at most c summation of I equals 2 to n I steps for some constant c. This sum is big O of n square. Insertion sort requires big omega of n square time in the worst case. It can be shown that this smaller bound holds in the average case as well. Linear timer sorting. 3 sorting algorithms are run in linear time. First one is counting sort or enumeration sort. Second one is radix sort. Third one is bucket sort. Of course, these algorithms use operations other than comparisons to determine the sorted order. Consequently, the big omega of n log n lower bound does not apply to them. Several algorithms that can sort n numbers in big O of n log n time, merge sort and heap sort, achieve this upper bound in the worst case. Quicksort achieves it on average. Moreover, for each of these algorithms, we can produce a sequence of n input numbers that causes the algorithm to run in big omega of n log n time. These algorithms share an interesting property. The sorted order they determine is based only on comparisons between the input elements. Such sorting algorithms are comparison sorts. In this section, we assume without loss of generality that all the input elements are distinct. Given this assumption, comparison of the form AI equals AJ are useless. So we can assume that no comparisons of this form are made. Assume that all comparisons have the form AI less than or equals AJ. The decision tree model. A decision tree is a full binary tree that represents the comparisons between elements that are performed by a particular sorting algorithm operating on an input of a given size. Control, data movement, and all other aspects of the algorithm are ignored. The execution of the sorting algorithm corresponds to tracing a simple path from the root of the decision tree down to a leaf. Each internal node indicates a comparison AI less than or equals AJ. Counting or enumeration sort. Counting sort assumes that each of the n input elements is an integer in the range 0 to k for some integer k. When k equals big O of n, the sort runs in big theta of n time. Counting sort determines for each input element x the number of elements less than x. It uses this information to place element x directly into its position in the output array. For example, if 17 elements are less than x, then x belongs in output position 18. We must modify this scheme slightly to handle the situation in which several elements have the same value, since we do not want to put them all in the same position. In the code for counting sort, assume that the input is an array a of 1 up to n, and thus a.length equals n. Require two other arrays. The array b of 1 up to n holds the sorted output, and the array c of 0 up to k provides temporary working storage. The below figure illustrates the counting sort. The operation of counting sort on an input array a of 1 to 8, where each element of a is a non-negative integer no larger than k equals 5. Figure A shows the array A and the auxiliary array C after line 5. Figure B shows the array C after line 8. Figure C to E, the output array B and the auxiliary array C after 1, 2 and 3 iterations of the loop in lines 10 to 12 respectively. Only the lightly shaded elements of array B have been filled in. The figure F shows the final sorted output array B. Counting sort routine shown in below figure. After the for loop of lines 2 to 3 initializes the array C to all zeros. The for loop of lines 4 to 5 inspects each input element. If the value of an input element is I, we increment C of I. Thus, after line 5, Ci holds the number of input elements equal to I for each integer I equals 0 up to k. Lines 7 to 8 determine for each I equals 0 up to k how many input elements are less than or equal to I by keeping a running sum of the array C. Finally, the for loop of lines 10 to 12 places each element A of j into its correct sorted position in the output array B. If all n elements are distinct, then when we first enter line 10, for each A of j, the value C of A of j is the correct final position of A of j in the output array, since there are C of A of j elements less than or equal to A of j. Because the elements might not be distinct, we decrement C of A of j each time we place the value A of j into the B array. Decrementing C of A of j causes the next input element with a value equal to A of j, if one exists, to go to the position immediately before A of j in the output array. How much time does counting sort require? The for loop of lines 2 to 3 takes time big theta of k. The for loop of lines 4 to 5 takes time big theta of n. The for loop of lines 7 to 8 takes time big theta of k. And the for loop of lines 10 to 12 takes time big theta of n. Thus, the overall time is big theta of k plus n. In practice, we usually use counting sort when we have k equals big O of n, in which case the running time is big theta of n. Counting sort beats the lower bound of big omega of n log n because it is not a comparison sort. In fact, no comparisons between input elements occur anywhere in the code. Instead, counting sort uses the actual values of the elements to index into an array. The big omega of n log n lower bound for sorting does not apply when we depart from the comparison sort model. An important property of counting sort is that it is stable. Numbers with the same value appear in the output array in the same order as they do in the input array. That is, it breaks ties between two numbers by the rule that whichever number appears first in the input array appears first in the output array. Normally, the property of stability is important only when satellite data are carried around with the element being sorted. Counting sort's stability is important for another reason. Counting sort is often used as a subroutine in radix sort. Radix sort. Radix sort is the algorithm used by the chord sorting machines you now find only in computer museums. The chords have 80 columns, and in each column, a machine can punch a hole in one of 12 places. The sorter can be mechanically programmed to examine a given column of each chord in a deck and distribute the chord into one of the 12 bins depending on which place has been punched. An operator can then gather the chords bin by bin, so that chords with the first place punched are on top of chords with the second place punched, and so on. For decimal digits, each column uses only 10 places. The other 2 places are reserved for encoding non-numeric characters. A d-digit number would then occupy a field of d columns. Since the chord sorter can look at only one column at a time, the problem of sorting n chords on a d-digit number requires a sorting algorithm. Sort numbers on their most significant digit. Sort each of the resulting bins recursively, and then combine the decks in order. Since the chords in 9 of the 10 bins must be put aside to sort each of the bins, this procedure generates many intermediate piles of chords that you would have to keep track of. Radix sort solves the problem of chord sorting counterintuitively by sorting on the least significant digit first. The algorithm then combines the chords into a single deck, with the chords in the 0th bin preceding the chords in the first bin, preceding the chords in the second bin, and so on. Then it sorts the entire deck, again on the second least significant digit, and recombines the deck in a like manner. The process continues until the chords have been sorted on all d digits. At that point, the chords are fully sorted on the d-digit number. Thus, only d passes through the deck are required to sort. Below figure shows how radix sort operates on a deck of 7 3-digit numbers. The leftmost column is the input. The remaining columns show the list after successive sorts on increasingly significant digit positions. Shading indicates the digit position sorted on to produce each list from the previous one. This figure shows the operation of radix sort. In order for radix sort to work correctly, the digit sorts must be stable. The sort performed by a chord sorter is stable, but the operator has to be wary about not changing the order of the chords as they come out of a bin, even though all the chords in a bin have the same digit in the chosen column. In a typical computer, which is a sequential random access machine, sometimes use radix sort to sort records of information that are keyed by multiple fields. For example, sort dates by 3 keys, year, month, and day. We would run a sorting algorithm with a comparison function that, given 2 dates, compares years, and if there is a tie, compares months, and if another tie occurs, compares days. Alternatively, we would sort the information 3 times with a stable sort, first on day, next on month, and finally on year. The code for radix sort is straightforward. The following procedure assumes that each element in the n-element array A has d digits, where digit 1 is the lowest order digit and digit d is the highest order digit. Below figure shows the radix sort routine. Bucket sort. Bucket sort assumes that the input is drawn from a uniform distribution and has an average case running time of big O of n. Like counting sort, bucket sort is fast because it assumes something about the input. Whereas counting sort assumes that the input consists of integers in a small range. Bucket sort assumes that the input is generated by a random process that distributes elements uniformly and independently over the interval 0, 1. Bucket sort divides the interval 0, 1 into n equal-sized subintervals or buckets and then distributes n input numbers into the buckets. Since the inputs are uniformly and independently distributed over 0, 1, we do not expect many numbers to fall into each bucket. To produce the output, simply sort the numbers in each bucket and then go through the buckets in order, listing the elements in each. Code for bucket sort assumes that the input is an n-element array A and that each element A of I in the array satisfies 0 less than or equals A of I, which is less than 1. The code requires an auxiliary array B of 0 up to n-1 of linked lists or buckets and assumes that there is a mechanism for maintaining such lists. The following figure shows the operation of bucket sort on an input array of 10 numbers, that is n equals 10. This figure shows operation of bucket sort of A, shows the input array A of 1 up to 10. Operation of bucket sort B shows the array B of 0 to 9 of sorted lists, buckets, after line 8 of the algorithm. Bucket I holds values in the left open interval I by 10, I plus 1 by 10. The sorted output consists of a concatenation in order of the list B of 0 up to B of 9. The below figure shows the bucket sort routine. To see that this algorithm works, consider two elements A of I and A of j. Assume, without loss of generality, that A of I less than or equals A of j, since floor of n A of I less than or equals floor of n A of j. Either element A of I goes into the same bucket as A of j or it goes into the bucket with a lower index. If A of I and A of j go into the same bucket, then the for loop of lines 7 to 8 puts them into the proper order. If A of I and A of j go into different buckets, then line 9 puts them into the proper order. Therefore, bucket sort works correctly. To analyze the running time, observe that all lines except line 8 take big O of n time in the worst case. We need to analyze the total time taken by the n calls to insertion sort in line 8. To analyze the cost of the calls to insertion sort, let ni be the random variable denoting the number of elements placed in bucket B of I. Since insertion sort runs in quadratic time, the running time of bucket sort is T of n equals big theta of n plus summation I equals 0 to n minus 1 big O of ni square. Analyze the average case running time of bucket sort by computing the expected value of the running time, where we take the expectation over the input distribution. Taking expectations of both sides and using linearity of expectation, we have the following result. We claim that E of ni square equals 2 minus 1 by n for I equals 0 up to n minus 1. It is no surprise that each bucket I has the same value of E of ni square, since each value in the input array A is equally likely to fall in any bucket. Define indicator random variables, which is shown below. Thus, ni equals summation of j equals 1 to n xij. To compute E of ni square, we expand the square and regroup terms, as shown below. Where the last line follows by linearity of expectation. Evaluate the two summations separately. Indicator random variable xij is 1 with probability 1 by n and 0 otherwise, and therefore E of xij square equals 1 by n. When k not equal to j, the variables xij and xik are independent and hence E of xij xik will produce 1 by n square. Substituting these two expected values, we obtain the following result. Conclude that the average case running time for bucket sort is big theta of n plus n into big O of 2 minus 1 by n equals big theta of n. Even if the input is not drawn from a uniform distribution, bucket sort may still run in linear time. As long as the input has the property that the sum of the squares of the bucket sizes is linear in the total number of elements, tells us that bucket sort will run in linear time. Selection sort. In the ith pass, we select the record with the lowest key among A of I up to A of n and we swap it with A of I. As a result, after I passes, the I lowest records will occupy A of 1 up to A of I in sorted order. That is, selection sort can be described by the algorithm shown in below figure. Example, list for selection sort shown in below figure. The passes of selection sort and the given list shown in below figure. Pass 1. The ultimate value of low index is 4, the position of Agun, which is swapped with Pele in A of 1. The lines in the above figure indicate the point above which elements known to be smallest appear in sorted order. After n-1 passes, record A of n, Vesuvius in above figure, is also in its rightful place, since it is the element known not to be among the n-1 smallest. Time complexity of the selection sort. Selection sort takes big O of n square time and will take big omega of n square time on some. In fact, on most input sequences of n elements. The inner for loop of lines 4 to 7 takes big O of n minus I time, since j ranges from I plus 1 to n. Thus, the total time taken by the algorithm is C summation of I equals 1 to n minus 1, n minus I for some constant C. This sum, which is Cn into n minus 1 by 2, is seen easily to be big O of n square. So, selection sort takes big omega of n square time in the worst case and the average case as well. Shell sort. Shell sort, named after its inventor Donald. It was one of the first algorithms to break the quadratic time barrier. It works by comparing elements that are distant. The distance between comparisons decreases as the algorithm runs until the last phase, in which adjacent elements are compared. For this reason, shell sort is sometimes referred to as diminishing increment sort. Shell sort uses a sequence h1 up to ht called the increment sequence. Any increment sequence will do as long as h1 equals 1, but some choices are better than others. After a phase, using some increment hk for every I, we have A of I less than or equals A of I plus hk. All elements spaced hk apart are sorted. The file is then said to be hk sorted. For example, the following figure shows an array after several phases of shell sort. An important property of shell sort, which we state without proof, is that an hk sorted file that is then hk-1 sorted remains hk sorted. If this were not the case, the algorithm would likely be of little value, since work done by early phases would be undone by later phases. The general strategy to hk sort is for each position I in hk plus 1. It goes up to n-1. Place the element in the correct spot among I, I minus hk, I minus 2hk, and so on. Although this does not affect the implementation, a careful examination shows that the action of an hk sort is to perform an insertion sort and hk independent subarrays. This observation will be important when we analyze the running time of shell sort. A popular but poor choice for incrementing sequence is to use the sequence suggested by shell. ht equals floor of n by 2 and hk equals floor of hk plus 1 by 2. The following figure contains a function that implements shell sort using this sequence. Worst case analysis of shell sort. Although shell sort is simple to code, the running time of shell sort depends on the choice of increment sequence and the proofs can be rather involved. The average case analysis of shell sort is a long-standing open problem, except for the most trivial increment sequences. We will prove tight worst case bounds for two particular increment sequences. Theorem Shell 1. The worst case running time of shell sort using shell's increments is big theta of n square. Proof. The proof requires showing not only an upper bound on the worst case running time, but also showing that there exists some input that actually takes big omega of n square time to run. We prove the lower bound first by constructing a bad case. First, we choose n to be a power of 2. This makes all the increments even, except for the last increment, which is 1. Now, we will give as input an array with the n by 2 largest numbers in the even positions and the n by 2 smallest numbers in the odd positions. As all the increments except the last are even. When we come to the last pass, the n by 2 largest numbers are still all in even positions and the n by 2 smallest numbers are still all in odd positions. The ith smallest number, I, less than or equals n by 2, is thus in position 2i minus 1 before the beginning of the last pass. Restoring the ith element to its correct place requires moving it I minus 1 spaces in the array. Thus, to merely place the n by 2 smallest elements in the correct place requires at least summation of I equals 1 to n by 2 I minus 1 equals big omega of n square work. To finish the proof, we show the upper bound of big O of n square as we have observed before. A pass with increment hk consists of hk insertion sorts of about n by hk elements. Since insertion sort is quadratic, the total cost of a pass is big O of hk into n by hk the whole square equals big O of n square by hk. Summing over all passes gives a total bound of big O of summation I equals 1 to t n square by hi equals big O of n square into summation of I equals 1 to t 1 by hi. Because the increments form a geometric series with common ratio 2 and the largest term in the series is h1 equals 1. Summation I equals 1 to t 1 by hi less than 2. Thus, we obtain a total bound of big O of n square. The problem with shell's increments is that pairs of increments are not necessarily relatively prime and thus the smaller increment can have little effect. Hibbert suggests a slightly different increment sequence which gives better results in practice and theoretically. His increments are of the form 1, 3, 7. It goes up to 2 power k minus 1. Although these increments are almost identical, the key difference is that consecutive increments have no common factors. We now analyze the worst case running time of shell sort for this increment sequence. The proof is rather complicated. Conclusion. In this chapter, we have covered the following in detail: bubble sort, insertion sort, selection sort, shell sort, Foster methods, tree sort, heap sort, merge sort, quicksort, linear timer sorting, counting or enumeration sort, radix sort, bucket sort.